Hi everyone, in this video I'm going to show you how to divide two complex numbers because obviously if you encounter a problem like this, there's no direct way to perform this division like there is with multiplication because there's no equivalent to the FOIL method for division. Now the key information that we'll need to remember in order to solve this problem is to recognize what exactly a complex number means and how it can be represented on a plane like this. So if I've got a number plane, then we can of course represent a real number by making a point somewhere along the real number line, right? But as soon as we've got an imaginary number, then we've got to represent it on this axis somehow. And if we get a complex number, then we've got to represent it as a point somewhere out here in space. So let's take the numerator right here for our number 1 plus 2i. That means we've got to go over to 1 and then go up to 2i, and that is our complex number right there. Similarly, if we look at this number here on the denominator, then we've got to go over 3 on the real number line and then go up 4 on the imaginary number line, like that. So we can represent these 2 points in the plane, like that. I'd like to point out that each of these lines that connect those points to the origin has a different length, and we can call it R1 and R2, and they also have an associated angle, which we can call theta 1 and theta 2, like that. The other key thing we need to remember to solve a problem like this is Euler's relation. And Euler's relation says that e to the power of I theta equals cos theta plus I sine theta. Right. The first step towards solving this problem, this division, is to convert these complex numbers into polar coordinates using their radii and their angle. All right, so the way to find the radii, so R1, for instance, is to recognize that R1 is equal to the x-coordinate of the number squared plus the y-coordinate of our number squared. So in the case of our numerator, that's going to be 1 squared plus 2 squared, and then the square root, because we go over by 1 and then up 2. So this equals the square root of 5. That's our R1. And then our R2 for the denominator is just 3 squared plus 4 squared, square root, and this happens to equal 5. Okay, next we need to get the angles, and there's a couple different ways to do this, but my favorite way is to get the arctangent. Right, so remember that if we've got a y coordinate divided by an x coordinate, this is equal to the slope, which is equal to the tangent of the angle that defines that slope. So we can say that the angle itself is equal to the arctangent, or the inverse tangent is what it's called sometime, the y-coordinate divided by the x-coordinate. So our first angle is going to be arctan of 2 over 1, or the arctangent of 2. After plugging this into my calculator, I find that this equals 1.107 radians. All right. Theta 2 is going to be the arctangent of 4 over 3. because it's the y-coordinate over the x-coordinate. And I calculate that to be 0.9273. Okay. We've got our complex number here. We can say that 1 plus 2i. Let's call this part the x part, and let's call this part the y part. Remember that using polar coordinates, we can represent x as r, the length of the vector, times cosine of the angle, and y as r times the sine of the angle. So I'm going to rewrite this complex number in terms of r and theta. So I get the square root of 5 cos 1.107 plus the square root of 5 sine 1.107, like that. Oh, and I'm forgetting my I right there. And now I can use the Euler relation right up there to convert this down here into a notation that just uses e. So it's going to equal the square root of 5, because I can pull that out, e to the power of I times 1.107, like so. Okay, let's do that for the next number here. In this case, my R2 is 5 cosine of my angle 0.9273 plus 5 times sine 0.9273 I, and this just equals, again using Euler's relation, 5 I times my angle 0.9273. Okay, so now I've got the complex numbers on either side of the fraction arranged in this form. So rewriting the original problem that's up here as a fraction, I get the square root of 5 e to the I 1.107 divided by 5 EI 0.9273. But remember that when we are dividing exponents, we can combine them together and it makes a subtraction up above the e. So this becomes the square root of 5 over 5 e to the I times 1.107 minus I 0.9273. Further simplifying this, square root of 5 over 5 e to the I 1.107 minus, that's a minus, 0.9273. This just becomes the square root of 5 over 5 e to the I times 0.1797. And there I've got my answer, but I need to still convert it back into the form a plus bi. And the way to do that is to do the Euler relation backwards. So this equals the square root of 5 over 5 cosine the angle 0.1797 plus square root of 5 over 5 sine 1797, like so, with my I. For this one, I'm calculating 0.4400 plus 0.07993 I. And that's it. That's how you divide two complex numbers. Okay, there is just one more thing I want to tell you about. Consider calculating the angle that defines the following complex number. -1 minus 2i. So when representing that number using my number plane, last time my number was over 1 in the positive direction and then up 2 in the positive imaginary direction, but now in this case I actually have to go the opposite direction. I go over 1 in the negative real direction and then down 2 in the negative imaginary direction. So as you can see, there's my angle for the number that I had before, but this is going to have to be the angle that I have for this number now that I'm considering. The problem will arise, though, when you go to calculate the slope from the arctan and you do -2 over -1, you'll see that this is going to be the exact same as arctan 2 over 1 because those negatives are going to cancel. And you're going to get the exact same angle, 1.107. And that's not good because the angle is not 1.107. The angle is a whole 180 degrees around. So we actually have to add pi to the angle. And so you actually have to do this yourself and look and see which quadrant your complex number is in and add pi to the angle if necessary. So I actually have to write 1.107 plus pi, and when I plug this in I get an angle of 4.249 radians. And that's the angle that I have to use for my complex number down in this quadrant. The same is true of complex numbers in this quadrant compared to this quadrant. Notice that both of those complex numbers have the exact same slope. So for this complex number down here, you've got to add pi to the calculated angle so that you do get the correct angle. You won't get the correct angle otherwise.